In the grand cosmic narrative, we are compelled to contemplate the evolution of the universe, from its mysterious inception to its hypothetical conclusion. This extraordinary odyssey captivates the mind with its immense scope and intricate tapestry of events. How did the universe come into being? What cosmic forces shaped its evolution? And what secrets does it hold about its ultimate fate? To grasp this journey, we must venture into the realms of cosmology, astrophysics, and theoretical physics, drawing upon established theories and conjectures to craft a meticulous and scientifically precise portrait of the cosmos evolution. Our tale commences with the epochal event known as the Big Bang that initiated the expansion of the universe nearly 13.8 billion years ago. At that moment, the universe existed as a seething hot singularity, an infinitesimally compact entity brimming with prodigious energy. As time progressed, the universe rapidly expanded, cooling in the process and giving rise to the fundamental forces and particles that would determine its destiny. In the initial moments following the Big Bang, the universe underwent a phase of swift inflation, during which it expanded at an exponential pace. This inflationary era is believed to have smoothed out irregularities and laid the groundwork for the vast cosmic structures we perceive today. The emergence of matter, antimatter, and radiation, coupled with the formation of primary elements such as hydrogen and helium, heralded the commencement of the universe's trajectory towards the complexity. As the universe unfurled its vast expanse, the primordial fireball that marked the beginning of our cosmic journey gradually cooled, allowing for a momentous transition to occur. This transition, known as recombination, was a pivotal juncture in the evolution of the cosmos, as it indicated the birth of the first atoms and liberated light to traverse space unencumbered. The epoch of recombination, occurring approximately 378,000 years after the Big Bang, set into motion a cascade of events that would leave an indelible mark on the cosmos. As protons and electrons combined to form neutral hydrogen atoms, the universe underwent a transformative shift. This shift allowed photons to stream freely through space, marking the birth of what we know as the cosmic microwave background, or CMB radiation. As these photons traversed the vast reaches of space, they have been stretched and redshifted by the universe's expansion, evolving from their erstwhile searing brilliance into the gentle microwaves we behold today. The striking uniformity of the CMB radiation, discerned to 1 part in 100,000, attests to the exquisite homogeneity of the early universe and provides compelling corroboration of the cosmic inflation, an epoch of hyper-expansion postulated to have unfolded within the first fractional moments of the universe's existence. CMB was first discovered in 1965 by Arno Penzias and Robert Wilson, and it emanates from all directions of the firmament at an exquisitely uniform temperature of approximately 2.7 Kelvin. The cosmic microwave background radiation is a relic from the earliest moments of the cosmic history, an ancient echo reverberating through the vastness of space. It serves as a celestial time capsule, capturing a snapshot of the universe at a time when it was merely a fraction of its current age. This cosmic afterglow, once unleashed into the cosmos, has journeyed across billions of light years to reach us, bearing witness to the ancient dance of creation. As we gaze into the celestial tapestry, we encounter the mesmerizing realm of stars, luminous beacons that illuminate the cosmos with their radiant splendor. Stars are born within colossal clouds of gas and dust, where gravitational forces sculpt these cosmic nurseries into dense cores known as protostars. Over eons, these protostars undergo a metamorphosis, igniting their nuclear furnaces and ascending to the lofty ranks of main sequence stars, the celestial engines that power the cosmos with their fierce brilliance. In their prime, these main sequence stars are steadfast sentinels of cosmic order, balancing the inward pull of gravity with the outward pressure generated by nuclear fusion in their cores. Yet as they exhaust their nuclear fuel, these stellar titans embark on a transformative journey. Some stars, like our own Sun, will expand into red giants, enveloping nearby planets in their fiery embrace before casting off their outer layers to form exquisite nebulae that will one day give birth to new stars and planetary systems. However, in a final act of cosmic majesty, some stars meet their end in a cataclysmic display known as a supernova, a resplendent explosion that briefly outshines entire galaxies. In this awe-inspiring conflagration, heavy elements forged within the crucible of stellar cores are scattered across the cosmos, enriching the fabric of space with the raw materials necessary for the formation of planets, complex chemistry, and life itself. These stellar remnants, neutron stars or black holes, stand as celestial monuments to the grandeur and impermanence of the cosmos. Galaxies, those swirling islands of stars and gas, are the building blocks of the universe, each one a testament to the power of gravity to bring together disparate elements into a harmonious whole. And yet, beyond the galaxies lie even grander formations, the galaxy clusters, vast conglomerations of galaxies bound together by their mutual gravitational pull, and the ethereal galaxy filaments, the largest known structures in the universe, consisting of walls of galactic superclusters. In the realm of cosmological evolution, the genesis of the first galaxies, galaxy clusters, and galaxy filaments is a tale of extraordinary magnitude. It begins in the primordial universe, a hot and dense sea of elementary particles and radiation mere moments after the Big Bang. As the universe expanded and cooled, small density fluctuations emerged, serving as the seeds for the future cosmic web. Under the force of gravity, these minute density perturbations began to coalesce, attracting surrounding matter and gradually forming pockets of higher density. Within these pockets, gas clouds collapsed under their own gravity, leading to the birth of the first stars. These massive stellar beacons ignited the darkness of the cosmos, marking the dawn of the cosmic starlight era. As these early stars exhausted their nuclear fuel and culminated in spectacular supernova explosions, they seeded the surrounding space with heavy elements and enriched the interstellar medium. Over time, these enriched clouds of gas coalesced into the first galaxies, each hosting billions of stars bound together by their gravitational embrace. Galaxies in turn congregated into vast clusters, driven by the relentless pull of dark matter and intergalactic gravitational forces. These clusters formed hubs within the cosmic web, sculpting the large-scale structure of the universe. The intricate network of galaxy clusters was interwoven by elongated tendrils of galaxies and gas known as filaments. They act as cosmic highways along which galaxies travel, drawn by the pull of gravity. The influence of dark matter extends far beyond its gravitational grasp, shaping the evolution and destiny of the cosmos. Through its profound influence on the distribution of matter, dark matter dictates the formation of the cosmic structures, orchestrating a cosmic symphony that unfolds over billions of years. As galaxies traverse these cosmic filaments, they leave behind subtle imprints on the fabric of space-time, tracing out the intricate patterns woven by dark matter's invisible hand. When galaxies come into close proximity, their gravitational fields exert a powerful influence on each other, through time culminating in dramatic collisions or graceful mergers. These cosmic encounters can result in the birth of new galaxies, as well as the metamorphosis of existing ones, fundamentally altering their structure, composition, and appearance. As galaxies merge, their constituent stars, gas, and dust are thrown into chaotic motion, triggering a cascade of star formation and the birth of new stellar generations. The resulting galactic hybrids may exhibit unique features, such as distorted shapes, tidal tails, and intense bursts of star formation. These interactions provide crucial insights into the nature of dark matter and its influence on galactic dynamics. A revelation of cosmic proportions emerged in the twilight of the 20th century, a discovery that would forever alter our understanding of the universe. Astronomers, armed with powerful telescopes and a spirit of unyielding curiosity, made an astonishing observation. The expansion of the cosmos, once thought to be gradually slowing down under the relentless pull of gravity, was not only persisting but accelerating. This discovery, born from observations of distant galaxies and Type 1a supernovae in them, unveiled a cosmic mystery that has captivated the minds of scientists, the enigmatic force known as dark energy. Dark energy, a beguiling and elusive entity, stands as a cosmic enigma that defies our understanding and challenges the very fabric of our scientific knowledge. Unlike ordinary matter and dark matter, whose influences are felt through their gravitational pull, dark energy exerts its dominion over the cosmos through an opposing force, an anti-gravity that propels galaxies away from one another at an ever-increasing velocity. This cosmic repulsion, born from the depths of space-time itself, has unshared in an era of cosmic acceleration, shaping the grand tapestry of the universe in ways that have left astronomers and cosmologists in awe. The nature of dark energy remains shrouded in mystery, eluding direct detection and confounding our attempts to grasp its essence. Despite its enigmatic nature, dark energy is believed to comprise a substantial portion of the universe's energy density, far surpassing the contributions of ordinary matter and dark matter. In fact, current cosmological models suggest that dark energy constitutes approximately 68% of the total energy content of the cosmos, casting a profound shadow over the fate and evolution of the universe. As galaxies recede from one another at an ever-quickening pace, the fabric of space-time itself stretches and distorts, sculpting a grand cosmic architecture that transcends the limits of human imagination. The web of cosmic filaments and voids is shaped by the interaction between dark energy and gravity, a drama that unfolds across billions of light-years. Moreover, the accelerated expansion driven by dark energy has far-reaching consequences for the future destiny of the cosmos. As galaxies are propelled apart at an ever-increasing rate, distant galaxies will eventually recede beyond our cosmic horizon, leaving future generations with a vastly different celestial landscape to explore. The death of the universe, a cosmic tragedy slowly unfolding across unfathomable timescales. What will become of the galaxies as they drift farther and farther apart, swallowed by the relentless expansion of space? What fate awaits the stars as they exhaust their nuclear fuel, succumbing to the darkness of a cold, lifeless expanse? How will the very fabric of space-time unravel in decay, leaving behind a desolate void, devoid of light and warmth? These questions probe the ultimate destiny of our universe, painting a haunting portrait of its demise. One of the theories that have emerged from the depths of astrophysical contemplation is the concept of the Big Freeze. At the heart of the Big Freeze lies the inexorable march of the cosmic expansion. As the universe stretches its celestial limbs ever further, galaxies find themselves adrift in a vast expanse, their distance from one another growing with each passing moment. This cosmic exodus, driven by enigmatic forces that defy comprehension, sets the stage for a profound transformation that will ultimately usher the era of the heat death of the universe. In the symphony of thermodynamics, entropy emerges as the maestro, conducting the gradual dissipation of energy throughout the cosmos. Like a cup of steaming coffee left to cool on a table, the universe relinquishes its vitality as energy diffuses into the void, leaving behind a landscape devoid of gradients and imbalances. In this state of maximum entropy, the very fabric of existence finds itself suffused with a homogeneity that extinguishes the flames of thermodynamic processes, rendering the universe an inert and lifeless tableau. Yet, amidst this cosmic elegy, other theories emerge, each weaving its own narrative of the universe's ultimate fate. The Big Crunch, a tantalizing hypothesis rooted in the dance of gravity and cosmic expansion, envisions a universe hurtling towards a cataclysmic finale. Like a cosmic rubber band stretched to its limit, the universe teeters on the brink of collapse, poised to snap back into a singularity that engulfs all in its embrace. And then there is the haunting specter of the Big Rip, an apocalyptic vision that pierces through the fabric of space-time with its relentless and unyielding force. In this scenario, the expansion of the universe accelerates unabated, tearing apart galaxies, stars, and even subatomic particles with an unforgiving ferocity. The very essence of existence finds itself rent asunder as the fabric of reality unravels in a cataclysmic maelstrom that leaves nothing untouched. In the epic cosmic tale, where time dances with space, the universe's destiny is a tapestry woven from scientific wonder and limitless imagination. Will it freeze into stillness, collapse in on itself, or be torn apart by unseen forces?